From this video, you might learn how to design and integrate ledge traversal actions into a game. This character can move along a ledge, can pull itself up, knows two attacks inspired by Souls games ladder combat, and can jump from one ledge to another. Practically, this already is a small core for an indie adventure game, but you haven't heard the punchline yet. These traversal algorithms are fully procedural. I have here no rails, no markers, and no arm hooks. I power my navigation with real-time asset geometry understanding. Give this character any cliff or building and it will be able to climb it. To start, general overview of our ledge action states family. Here we have our central class of ledge grab. Ledge grab is a complex state of several substates, as it can be in an idle pose, it can traverse the ledge left and right, and it can be in a state of traversing an angle between two ledges, which is often a separate animation. Ledge grab then have several external transitions. We can let go of ledge and fall if go down action is inputted. We pull ourselves up if player inputted go up action, and the input vector relative to camera points towards the ledge. If go up action is inputted while input vector doesn't point towards the ledge, and we sense another ledge we can jump to in close proximity, we do a ledge to ledge leap. If go up action is inputted but neither pull up, no ledge leap can be done, character performs the wall jump action. Finally, we accept attack inputs to perform two attacks that are specific to our ledge position. Both attacks and ledge leap play their animations and always return to the ledge grab in the end of their life cycle. Now let's look at the ledge grab script. Right from the first glance onto it, you can notice its deviation from the norm. Usually I try to design with concise scripts. However, this monstrosity has almost 200 lines and rivals the core ancestor class itself. This volume comes from two sources. First, as ledge grab is a nested state that owns several substates, it houses the code for all of them. Second, there is a lot of very low-level stuff that needs to be done but can't really be hosted anywhere else. Now, before talking about what happens here, I want to make a short brief of the terms I use to describe the logic of the state. First, the current ledge. This is a variable that is stored in area awareness module to be accessible from the rest of the game, and to describe the ledge we are bound to. The ledge is described as an array of two vector3 values representing ledge's vertices. Next is grab point. It is rare for this parameter to be named explicitly. Usually it comes in the form of this vector or one of its components. What is probably a magic number anti-pattern and must be fixed, but whatever, apparently. This vector represents this point right here, the point between our character's arms in the ledge hanging pose. And finally, the grab direction vector. This vector is the altitude between the ledge we are hanging on and the vertical vector starting from character's position. And with this vector, I actually want to discuss a small technical debt I left behind the last episode. So, this is the old code for grabbing a ledge, and this is the new one. What old code does is it just projects an altitude from character positions onto the ledge, then projects this vector onto horizontal plane and calls it a day. It seems nobody caught me, including myself, but this approach actually is bullshit because it works only for horizontal ledges. If we'll try to use a non-trivial ledge direction, our altitude will return us some totally unrelated point that can be bound to our grabbing point anyhow. So to fix this, we need to defy the laziness and to do proper solution to find the altitude from the ledge towards our player's spine. Bad news is the problem it's not so trivial. Good news is the problem is actually classical IF you could note by the different name of finding the shortest distance between two lines in three-dimensional space. I don't want to waste too much on this, so galloping. One of the ways to describe a line is to provide a point that line contains and then to provide a vector aligned with this line. Adding some amount of this vector to the first point will result in ability to describe any point of the line with a certain coefficient. Our ledge line is described as one of its vertices plus some amount of the vector from one ledge vertex towards another. Our vertical axis is described as character's position and some amount of vector3 ups. Now, in one operation we can get the direction of the altitude we search for. We do it by taking the vector crossing of two vectors that describe our lines, and we do it because vector crossing operation always returns a vector perpendicular to both operands. Having this direction, we can say that distance between two lines is the distance between two points that belong to these lines, but are projected onto our altitude containing line. And because of how vector projecting works, a lot of stuff gets deleted, and we have here a nice formula. Now when we know both direction of our altitude and its length, we practically have a concrete vector. And because of how some triangles work with a system of two equations and two variables, we can calculate these points as follows. If you didn't understood anything, not a problem, I left a link here with more materials and I will duplicate it in the description. Let's move to the code. First, external transitions. This transition code right here is almost completely synced with the description I gave in the start of the video, word for word. Go up, go down, attacks. But on top of that I have a big silencer condition. There are two substates of our lifecycle that just prohibit external transitions. These substates are correction and angle traversal. This will be my bridge to substates. We have 4 of them. Correction is the substate of being in the first 0.3 seconds into the state. During this period we don't accept inputs, we don't do no external transitions, no internal ones, and we don't move. Instead what we do is we correct our posture to properly hang from a ledge, because we can initiate the grab from a bunch of different positions in the world, but we hang from it in a strictly defined pose. Next one is idle substate. This is the idle pose for our ledge grabbing family. Essentially we just hang. Traverse is the quotes walking state analog. We accept directional inputs and we move along the ledge with this slow animation. And the last substate is reserved specifically to angle traversal. This move we do when we moved along the ledge far enough to go further than our shoulder's width, but simultaneously we have another suitable for grabbing ledge after the current one. By far this is the most interesting and complex substate, and I will talk about it for long in its own section. Now, a very important topic. Animations. Look at my update function. We choose direction, it's an internal function to prepare the frame. We then choose substate, and then as absolutely separate thing, we choose animation. I stress your attention on that because usually we think of our states as of separate animations, but here these borders blend heavily. Our correction substates uses our idle animation but moves, our traversal substates actually has 2 animations for one logic, and our angle traversal substates might and probably must use a separate animation, but does use traversal animation as well, but it is uninterruptible. So, for ledge grab specifically, try to abstract from animations altogether and think in logical substates instead. And from here I think it's more logical to slice the explanation by substates instead of by functions, so let's begin from the simplest one, idle. We end up in this state either if input vector is 0 or if input vector exists but points towards the end of the ledge we can't traverse further. Idle substate animation is, well, idle animation, and idle substates update logic is non-existent. Correction. We end up in correction state independently of input vector in the first frames of ledge grab lifecycle. During update step we do 2 movements. First we slightly move in a way we align our logical ledge grabbing point with our logical between arms point, and secondly we slightly rotate our character to align our bases with the grabbing direction. Traverse. We end up in this state if we get a command to move and we have enough place to move in said direction. And here I must finally mention this choose direction method. In fact, choose direction method is sort of more important than choose substate, and it comes first, because when we hang on the ledge, our existence is relative to the ledge direction. This also applies to the input direction as we often want to project it onto ledge segment or do some similar operations. So here I compare input vector with ledge direction, and if they are co-aligned, I set the next point parameter. This parameter can take only 3 values: 0, 1 and -1. This as well might be considered a magic number fallacy, but I really like the further usage of this parameter. So -1 is nowhere, in other words we can say that input logically points towards any ledge vertex, and then 0 and 1 values determine to what exact vertex do we crawl, because our edge is an array of 2 values and indices of that array are 0 and 1 for numbers of the element. So if the next point parameter is 1, it means that input vector was aligned in a way we want to crawl towards the point in that large array that is stored as a value number 1. And this operation is done here as the first thing we do in the frame because we use this parameter often further down the line. For example, here a syntactic sugar function in internal transition logic, ledge distance to chosen vertex. This construction, as I told previously, is our code for grabbing point, and it obviously is laying on the ledge, and then we return the distance between this point and the point on the ledge that has an index of next point. Ta-da! And then we compare it with shoulder width to determine if we can crawl further. And when we update traverse and substate, we first need to calculate velocity, and we do it by so in different operations we routinely need one of the ledge directions. And because our points are described as 0 and 1 indexes, we can achieve it with a smartass operation of +1 mod 2, because it flips 0 into 1 and vice versa. So this lengthy line just tells move along the ledge towards one of its points. I also stress your attention on that we name this parameter as velocity, but we never move and slide. We just position plus equals velocity because this movement is not meant to be a physical interaction. And finally, the angle traversal substate. Starting from the internal transition, if we get to this line, it means that we're already moving along the ledge, but distance between our grabbing point and chosen point is less than our shoulder's width. So the next obstacle, we need to look if we have another climbable edge in the direction we go. To do this, once again, we need to use the help of our great geometry data baking technology. If you forgot how it works, please rewatch the previous video in the series. And expectedly, to parse a list of neighbor edges, we first need to create it somewhere. So here we are, right neighbors and left neighbors. And then the next immediate thing you will see here is that I ask for this data by an integer parameter, edge ID. Yeah, full circle, ladies and gentlemen. We came back to integer IDs to select an edge, and it is almost comically funny because here I have two giant ass ugly duplicated data structures, edge to ID and ID to edge, which is essentially the same thing, but we sort of can't have a hash map with both things being keys. So why do I suffer this humiliation of a design right here after I spent so much time writing my things previously via direct edge vertices coordinates? Well, here's our Greek tragedy of different world views. There is assets local world, and in it we store all its geometry data, and there is our global world in which most of our logic during execution work, and between them there is a firewall, the river Styx, a mathematical operation of no return. We can ask an asset to describe us a ledge, and we do it by taking asset's local coordinates of its vertices and multiplying them by asset's global transform. From math's perspective, the operation is not destructive, and we can take ledge codification in global coordinates and multiply it by an inverse global transform of an asset. However, in reality, this operation fails due to float precision problems, and as we need 6 float numbers to be translated 2 times without any losses, we are doomed. You cannot restore edge's local coordinates if you have its global coordinates, and it means that you cannot access any data that uses local edge coordinates as keys. We already used global to local translation here once when we used surface normals as keys to faces map, but in normals case there are several small mitigating circumstances that all add up to us being able to just round normals up to the last 2 or 3 digit spots dot. For normals we transcend the def once, we use 3 floats instead of 6, and the cost of failing to find a normal is only 1 frame malfunction, because during the next frame the scanning ray will try to read this normal NU and may return it without physical error. But for edges we need to transpose 2 times, do it with 6 variables, and the price of mistake is not 1 frame but a forever broken edge. If it loses connection, it's gone forever unless an asset somehow moves. So it comes clear that vector3 data can't be used to go back and forth through this local coordinate singularity bubble, and we need to find a key that is immune to such conversions. And, well, the oldest trick in the book, an integer ID can be such a key. So now, during our baking process, we assign an integer to every codified edge. However, internally, geometry data still wired via vector arrays, because it's just a nice data structure where both keys and values have the main sense, and I don't want to turn this all into some entity per ID database. And the original method that communicates as arb edge back now returns 4 vectors array, where, yeah, 4 vectors x coordinate holds edges ID. I know, awful, but I really like vector array structure for previous data transfers. Using 3 vector array to send segment as 2 points plus intersection point with scanning plane is just too beautiful. If I will need to send another 5th variable, I will cave in and I will create a resource to hold a proper edge data transfer object. Now, did you think low-level bullshit ended here? We are only trying to transition into angle substate, but right here on the next line lays another trap. To smoothly tailor our animation, we need the future grab direction. In other words, the direction towards our character needs to look at the moment of exiting the angle traversal in the end. And the task is not trivial. Your brain will try to bombard you with a bunch of cheap and fast solutions, like just taking some crossing, using the knowledge of do we go right or do we go left, or checking the future positions against the plane that holds current ledge, etc. But none of those easy approaches will work because we need an algorithm that will be immune to edge vertex indexes placement in array because of how our data works, to internal and external angles because we want to traverse all kinds of surfaces, and to symmetrical translation because we want to traverse left and right. And here we have 8 places for your easy solution to break due to random vector crossing flipping, and the task that seemed to be one-liner becomes depressingly intricate. So what we do is we forcefully straighten our edges locally, just for this time. We have the next ledge as 2 points, but we don't know the direction of the vector. So first we find what index in the next edge is the point that is common between our ledges, and then we specifically construct 2 vectors for our ledges that will be co-oriented relative to the common point. And when we guarantee that our ledge vectors are co-oriented, we can guarantee that vector crossings of those vectors with vertical axis are also oriented consistently relative to this wall. And then we check one final time to see if we use our current grab direction as a template or minus current direction. Yeah. Next, animation. This seems like an easy possible part, but I want to stress your attention that this piece is the pinnacle of my work around the wall angle traversal substate. Despite right here my angle animation is exact same as simple traversal, because I don't have any animations, I sweat my ass to detach the logic of angle traversal from everything else as clean as I can, because in this case I can integrate a true angle traversal animation here with finger snap easiness as soon as I get one. Finally, angle motion logic. We have an angle traversal timing, we have current and next grab directions, and we have 2 linear measurements, our shoulders width. So during the angle phase I do 2 parallel movements. First one is movement of character in a way its grab point will cover exactly 2 shoulder widths over the period. And the second one is rotational in a way we will turn gradually to face the next grab direction when the turn ends. So each frame we calculate current progress of our quads animation, calculate new basis, new origin, and update the timer variable. And in the end, if our time variable exceeds quads animation duration, we reset everything, exit angle substate, and make all variables that describe current edge to describe the edge that was next edge just a moment ago. Now, before we throw ourselves at ledge leaping, let's first relax with some simpler side secondary states. Pull up and do attacks. For attacks, they are actually sort of fraud, sadly. As you can see, they are literally just empty states that play animation and return to the ledge grabbing state. This is due to me being lazy to set up 2 new weapons for parkour project, and the transition is somewhat botched due to our combo system being deconstructed right now. We do everything through code, but I gathered some experience here and I am fairly certain I will soon be able to reintroduce the renewed combo system that will facilitate easily itemized input mapping back into our system. And pull up? Well, as you see, it has some issues. The reason is root motion track being garbage, but to construct a nice animation is not a trivial task. Look, when we hang, Our root bone relatively to the player's position, i.e. the floor, is on about 1 meter height. However, when animation ends, root bone needs to be close to the floor, and simultaneously we need to say if our hands snapped to ledge in IK fashion. So constructing root motion track for such an animation is a non-intuitive task, what I can't truly do nicely. I just slapped here a linear motion to negate skeleton's movement. Yeah, well, you get what you pay for. At least I spent like 3 minutes on it, and in the end you will ask competent people for help when you need it anyways. Now for the final charge. Ledge leaping. The task is actually almost complete by our previous achievements. Remember how we searched for climbable ledges with a small detector plane? Well, we could do it again, only this time the plane will be bigger and it will look in the direction of the input vector. See, I input my DK to set directional input to point to the right. I press jump and the huge plane scans for climbable ledges in that direction. But we also have some minor tweaks. For example, we install here a small defensive mechanism against triggering on a ledge we already hang from, and we also skip searching for altitude. Instead, we just set the grabbing point as is on the intersection between the ledge and the plane, and only care about it being inside the safe space considering our shoulder width. There is though the last bit of complexity. Yeah, surely my animation, again, is just a proxy, but I wanted to give it some minimally nice feel. So, rotation-wise, we just turn towards the next ledge during the flight, but positioning is interesting. In the most simple model, thrown bodies have their trajectory described as parabolic curve, and I want to replicate that. So, what is the easiest way for us to code down a two-dimensional parabola into 3D space? Well, luckily, this is not some random parabola, as it has some nice properties. First, let's solve the problem just on a plane. We know 2 points in the trajectory, our initial leap position and our final leap position. To make things easier, let's also count from initial leap position so our parabola contains the zero of Cartesian system we live in. We will code final leap position coordinates as XL and YL. Nice. But not enough, because 2 points set an infinite number of curves. To set one in stone truly, we need a third parameter. And to make life easier for our artistic directors, animators, etc., I chose the third parameter to be, quotes, height overshoot of the jump. The difference in height between the highest trajectory point and the final position. That way we will make our animation highly customizable with one number parameter that is easy to understand. Now, any parabola has a peak, let's call its coordinate as xh and YH, and then just start to read the picture. Firstly, as our parabola traverses through 0, the C coefficient is also 0. We also know that both final position and peak points submit to the parabola equation. Now I will get rid of YH by saying it is actually just YL plus H, and then I will get rid of XH by saying it is actually minus B divided by 2A. From here I fear cheating is over, so first I will express B as a variable and put it into the second equation, leading to this monstrosity you see on the screen. This is quadratic equation relative to A, and we can solve it with the oldest trick in the book. From here all the dirty work is done by a machine, and as the equation is quadratic, we get a parasitic root, so to choose between them we choose the one that gives us peak x coordinate that is between the points. From here, life is easy, we have Kerr's formula, so we just sample it with horizontal distance between our initial position and our end position in 3D space. And our designer gets to play with sliders. That's it, thanks for watching, I hope you didn't lost humanity during this maths heavy episode, and as always, I cling to mine thanks to my wonderful patrons who support this catastrophe of a channel. I'm pretty satisfied with how this one came out, aside from one aspect. Algorithms are cool and all, but yeah, our Indiana Jones looks like some game from 30 years ago. With this level of visuals, we can never achieve the sacred goal of showing Unreal Engine fanboys their place, so in the next parkour episode, I want to finally visit the theme of inverse kinematics for animation. But before we can do that, I need to introduce some slight changes to how this project deals with skeletal animation.